are some formulas for you. So first of all, this is the equation for the tangent plane. To the surface z equals f of xy. Okay, so so you have the xy plane, right? And then you have a function of points in there, and so that's going to give you a point. So basically, here's the xy plane here, and here's the z. And so for each point down in this plane, you're going to have a point. You're going to have a value f up here. So it's going to be some kind of a surface, okay? And if you're looking at that surface, then at any point on that surface, there's going to be a plane that is tangent to that point. And this is the equation of that plane. So you have a point x naught, y naught, z naught, x naught, y naught, which you plug into here, get z naught up here. There's going to be a plane tangent to the surface, to the z surface at that point. Okay, and that plane is going to be sort of around that point. It's going to be sort of an approximation, because at the point it's going to be at the point that it's going to intersect with the function, the surface. Okay, and then close to that point, it's going to be close to the surface. I don't know, maybe I should have put a picture to kind of visualize that. But anyways, if you take this z naught to the other side, so the way that the z naught is obtained is by plugging x naught and y naught into here. So this right here is really f of x naught, y naught. Okay, so if you take this to the other side, and then we do everything in a's and b's and whatever. So this is just taking the z naught to the other side, okay? That's just taking the z naught to the other side and the linearization. So basically, if you just take this to the other side, then you have the linearization, okay? And this is an approximation. So when xy is close to AB, so this case it's AB, and then over here it's x naught, y naught, right? So this is AB. When xy is a point that's close to that, then z, or we'll say not z, we'll say f of xy is close to the linearization, okay? So that's just the tangent. This is just the tangent plane, basically. The points on the tangent plane, and this is comparing it with f. So they're going to be close when you're close to the point where you take the tangent plane. Okay, this guy right here is called the differential. And that's, you just take the partial with respect to x, tack on a dx. Partial with respect to y, tack on a dy. This is also sort of an approximation. And the actual change in z is this, is the difference between f of x plus the difference in x, y plus delta y minus f of xy. And the differential is approximately equal to, is an approximation for the actual difference. Okay, and so we'll get to some problems based on that a little bit later. Okay, let's go to the homework. And number 1 is to find an equation of the tangent plane to this function here at the point 1, 4, negative 18. So notice that if you put a 1 and a 4, if you make x naught equal to 1 and then y naught equals 4, then z naught is going to be 2 times 1. I'm just following this equation here. plus 4 squared minus 9 times 4, and that's going to be what, 2 plus 16 minus 36. This is going to be negative 18. Okay, so that gives you this one here. So those 2 points were used to get this third one, this third point. Okay, and so then there's going to be a tangent plane to the surface at this point. And according to the previous page, this is the equation for that tangent plane. So first of all, let's take the partials, the partial with respect to x, partial with respect to y. Okay, and then we'll evaluate those at x naught, y naught. And that should, then we'll plug it into the formula. Okay, so all this is like my f of xy. So partial with respect to x, what's partial with respect to x?
4x squared, 4x.
4x, good. And if you take 1 and plug in, make x equal to 1 and y equal to 4, that's going to give you
4.
4, right? And what's fy?
It's going to be 2y.
And fy of 1, 4.
Wait, what about the minus 9?
Oh yeah, minus 9. Okay, so okay, and if you plug in a 1 for x and a 4 for y, you get what? Negative 1.
2, 4, negative 1.
Yeah, negative 1. Okay, so then plug in, using the formula, z minus z naught, that's going to be plus 18.
Plus 18.
Equals fx, which is 4, times x minus 1, minus 1, which is like, you don't have to write that, and then y minus 4. So there's the equation right there, but let's simplify it. Or should we simplify it, or just leave it like that? Think we can get away with it, just leave it like that? Or should we
Maybe
expand this out? What do you think?
we should try.
Sure, let's try. Okay, let's see what happens. I got away with it. Did you guys? So yeah, it accepted this answer.
Yep, got away with it.
Okay, now, number 2. It says, explain why the function is differentiable at the point 2, 4. And differentiable means that, so in this context, differentiable means that the partials, the first partials, or all the first partials. In this case, there's only going to be 2 because it's the equation in x and y. So differentiable means these exist and are continuous at 2, 4, the point AB. Okay, that's the definition of differentiable. Okay, what it does not mean it has a derivative. Now, of course, it's going to have partial derivatives. So basically, it just means it has partial derivatives and that those partial derivatives are continuous. So it does not mean it has not a one thing that's a derivative. Okay, because that doesn't happen. Okay, so fy. So here's our function. What's the partial with respect to y? Well, that's going to be 0.
1 over y.
I mean, 1 over all this, right?
Oh,
And there's x there too. So, and then what's the derivative? What's the partial of this with respect to x? I mean, with respect to y. I'm sorry. Wait a minute.
X minus 7.
I was supposed to do the. What's that?
The inside is just x minus 7.
I thought it's just x because this is 0.
gonna be
So
0.
it's going to be x squared over that. Right? Okay. So okay, I missed this part here. Darn it. Okay, I missed that. Hold on. I missed that part. Okay, so the partial with respect to x. Okay, that's 0. This is going to be ln of xy minus 7 plus x times the partial of this with respect to x, which is xy minus 7, and then it's going to be xy. Okay, so I believe that's what it is right there. So let's see. Or did I make a mistake somewhere?
No, we're good.
Okay. Okay, something to write that a little bit better. Okay, let's see if that works. So ln of xy minus 7 plus xy over xy minus 7. And then the other one is x squared over xy minus 7. Okay. Okay, so that says it's okay. And then they also want us to calculate f x of 2, 4. Okay, because it's a 0.24. So that means you're going to put a 2 in for x and a 4 in for y. So that's going to be log of 2 times 4 minus 7. Hey, that's log of 1, which is going to be 0. That's all going to be 0. Plus 2 times 4 over 2 times 4. Hey, that's also 1 down there. So that's just going to be 8. And then fy of 2, 4 is going to be 2 squared over, and that's all, we already said that's 1, so that's 4. So 8 and 4, let's try that. Okay, both fx and fy are continuous. So that's 2 different answers, and then that's that one there. For xy greater than something. Okay, so if you have xy, so the problem that you're going to have is this logarithm part. So this is a logarithm part. Okay, so first of all, here it can't be 0, right? But here it has to be greater than 0. So, because you can't take logs of 0 or negative numbers. So this has to be greater than 0. And so that translates to this, greater than 7. So it's going to be continuous if the product xy is greater than 7. And the product here is 8. So we're good. 2 times 4 is 8. So so it's going to be continuous there. So we are good with that. Okay, so that's the first part, and that's part A. Part B says to find the linearization. Okay, remember that one's going to be f. That's f of AB, or f of 2, 4, plus the partial. Wait, rather than write that down, rather than do that, I'm just going to write down what it is. So it's the value at 2, 4. Whoa, we never figured that out. Okay, so yeah, it's f of I had to write that down anyway. Okay, so let's figure out what f of 2, 4 is, though. So that's 3 plus 2. I'm just plugging it into here. Log of 2 times 4 minus 7. That's good. That's log 1. That's all 0. That's all 0. So it's just 3. Okay, so that means that the linearization at this point is going to be 3 plus the partial of x, which is 8 times x minus 2 minus x naught, plus the partial of y, which is 4, times y minus y naught, y minus 4. Okay, so that's the linearization right there. We can see if they'll accept that. I don't know. Yeah, it accepted it. Okay, so once again, this came from this formula here for the linearization. So the value at the point plus the partial at first, the partial with respect to x at the point times x minus the x coordinate plus the partial of f with respect to y, evaluated at the point times y minus the y value of the point. Okay, number 3. Find the linear approximation of this function at 623 and use it to approximate this number here. Okay, so I guess the easiest thing is just put this in the calculator, but you're not allowed to do that. You're supposed to do it using the linear approximation of this function. Okay, and that is the linearization. Okay, so that means that the first thing we should do, and now this one is a little bit different. It's taking it to another level, sort of, because you have a fourth variable. So these are there are 3 variables here. There's 3 variables, x, y, and z, that are independent, and then w or this could be considered the dependent variable. So 3 independent variables, whereas in the previous problems we'd only had 2 dependent variables. So then you would say, okay, this one there's not going to be a tangent plane because it's going to be more like, because it's going to be something. So the tangent whatever, if you could call it something, if you call it a tangent something, it would be 3-dimensional, okay, instead of 2-dimensional. So plane is 2-dimensional, but this is got to be 3-dimensional because there's 3 independent variables. But the linearization pretty much extends. So this would be the w naught, and then the partial with respect to x times that, partial with respect to y, and then you'd add on a partial with respect to z times z minus c or something like that. Okay. So we're doing it at this point right here. So first of all, the first thing to do would be to calculate f of the point. So that's going to be what goes on the front of the equation. Okay, so we can do the linearization down here, or maybe, yeah, we can do the linearization there. Okay, so after 623, that's going to be what? The square root of, and square each of these, so that's 36 and 4 and 9. So it's the square root of, that's 7. Okay, so good. We're leading off with 7. Okay. Then the partial of x with respect to x. Okay, and then this could also be written as x squared plus y squared plus z squared to the 1/2. Okay, so it's the partial with respect to x. And this.
It's gonna be half times.
Yeah, 1/2 comes out.
Yeah, times x squared plus y squared plus z squared. And then negative half
And then you read it. Yeah, to negative half. Okay, and then
plus 2x.
yeah, so it's gonna be times
Times
2x.
2x.
Okay, now these two are gonna cancel, right?
Mm-hmm.
So we get that. So we basically get x over the square root of x squared plus y squared plus z squared. And if you plug in the 0.623, you're gonna get what?
So the
The
bottom one is
numerator
going to be
is
7. 6 over 7.
yeah. Yeah, so that's gonna be 6 over 7. Okay, so then we have 6 over 7 x minus 6. Okay, what do you think the next one's gonna be? Does anybody want to take a quick guess at it?
Y.
What do you think fy of 623 is gonna be?
It's going to be, so 4 over, no, 2 over 7.
2 over 7, right? Okay.
Yeah.
Because this thing's symmetric, right? It's x squared plus y squared plus z squared. So these are kind of on equal footing. So when you do the partial with respect to y, then it's going to end up with the same thing except for y up here. So 2 over 7. So that's going to be 2 over 7 times y minus 2. And then the last one,
3 over
is
7.
3 over 7. Z minus 3. Okay, so there's the linearization. And we're supposed to use it to calculate that. So basically L of 6.03, 1.98, 2.99. So that's going to be 7 plus 6/7. If we put a 6.03 into here, we're going to get 0.03. And then we have 2/7 times, if you put a 1.98 in here, then we're going to have negative 0.02. And this one's going to be negative 0.01, right? So 7 plus 0.18 minus 0.04 minus 0.03 all over 7. So what is that? 7 plus 0.11 over 7. Okay, let's try that.
7.
It looks like we're supposed to round to 5 decimal places. So 3 times, no, 7 plus 0.11 divided by 7. And I get approximately 7.01571. The next one is a 4, so that stays as a 1. Okay, let's see if that's the answer. Oops.
Brother Hurst, where's the,
Yes.
I see it. I thought I saw it wrong.
Yay, I'm glad to have answered your question. Okay, that's interesting. So now, are you curious to know what this actually is? If you plug it into the calculator? Anybody curious to know that? Or you're like, nah, I don't care.
Is it gonna give us the same answer if we just plug it in?
Well,
try.
let's see here. I did it, and it's 7.0157. Wait, 796. So let's see here. It looks like it's okay up till maybe here. Looks like it's okay up to here. And then this next spot, this would round up to an 8, but that would round down to a 7. And the next spot. So it looks like we're good to, we're not good till further decimal places. Okay, now let me just say something. Part of the reason for doing this sort of thing is that this is the beginning of how the calculator does things. Okay, so the calculator doesn't have, so to find a square root, it sort of does a similar algorithm here. Because you only have the basic operations, addition, subtraction, multiplication, and division, right? Those are the basic operations. And to get anything else, you have to do some combination of those on your calculator. Okay, or use some program that does a combination of those things to get other answers. Okay, and so this is sort of the beginning of heading down that road of being able to use a calculator to actually get, you know, really, really accurate values for things like this. This is sort of just heading down the road in that direction. Okay, so let's go on to number 4, find the differential. So the differential was basically, you just take the partials and then tack dx's or dy's or whatever. Here it would be dp's and dq's on the end of them. Okay, so what's the partial with respect to p of this?
Respect to p, it's gonna be
Yes.
5p to the power 4 and p7, q7 to the power 7.
And then dm dq
7
is going to,
q to the power 6.
right. So the differential is okay, you take this one, change it to dm. You put this and then put a dp there, plus this one, and you put a dq there. Okay, now in Webassign, they already have the dp and dq there, so you only have to put the partials. Okay, so mine says it was right. So let's move on to the next problem. And we're going to compare values of delta z and dz as you go from this point to this point. Okay, so first of all, delta z, that would be, so if this is our f of xy, oh, this is f of xy, then delta z would be f of the second point minus f of the first point. Like that. Okay. So let's see, plug in 1.05 for x and a 2.9 for y. And that's your f of 1.05, 2.9. And then you plug in a 1 for x. And then a 3 for y. It says round to 4 decimal places. Let's see. So go ahead and plug that into the calculator.
I got negative 0.0775.
775?
Yeah.
Let's see. Okay, that's the second answer, actually. Negative 0.0775. And Webassign says, yes, it is. Okay, now, for the DZ, what we do is you calculate the differential. Okay, so the differential would be 10. So it's the partial with respect to x, which is 10x dx. And then the partial plus the partial with respect to y,
2y.
which is 2y dy.
dy.
Okay, now what you do is we're going to use this first point and plug in the first point there. And then for the dx and dy, we're going to use this. So it went from 1 to 1.05. That means your dx is 0.05. It increased by 0.05. Okay, and then here it went from 3 to 2.9. So that means it's a
0.6.
decrease of what?
Is it?
From 3 to 2.9.
Oh, sorry.
That's it.
1.
Decrease. Yeah, decrease of negative 0.1, right? Okay, so you calculate what that is. So 10 times 0.05 minus that's weird. I get a negative 0.1. Okay, and Webassign agrees. Okay, so there's your two answers right there. Okay, then the last problem is use differentials to estimate the amount of metal in a closed cylindrical can that is 14 centimeters high and 10 centimeters in diameter. If the metal in the top and the bottom is 0.4 centimeters thick, and the metal on the sides is 0.05 centimeters thick. Okay, so we have a closed cylindrical can, something like this. So it's closed on the top and the bottom. And what you want to do is think about it this way. The way that you think about it is, if you were to so you can think of inside the can, there's a cylinder that starts. If you go from the inside of the can, there's a cylinder, and then from the outside of the can, it's a larger cylinder. And those two cylinders. Okay, so if you go outside the metal, on the surface of the metal on the outside, and go all the way around the can, that's a cylinder, the right cylinder. Okay, but then also if you're inside the can and you go on the surface of the inside, that's another cylinder. Okay, and if you take the largest cylinder and subtract the volume of the larger one, subtract the volume of the smaller one, then you're going to get the volume of all the metal. Okay, does that make sense?
Yeah.
So that means what you want to look for is the volume. Okay, so here you have height and you have radius, right? Okay, what's the volume of the entire can? Okay, so you can start by taking the area of the top, the area of this circle here on the
Times
top,
height.
times the height. So the area of the circle is pi r squared, and then there's the height h, right? Okay, now dv, the differential. Okay, so you have volume is a function of radius and height. So what's the differential?
Are we differential according to 2 pi r
Yes, 2 pi r h
t
dr.
r
That's here, and then plus. Now you take the
pi
partial
r
respect to
square th.
dh. Yes. Okay. Yes. Yes. Exactly. Okay. So now what we're going to do is we're going to plug in everything. R is okay. So the diameter is 10. That means that R is 5. So you're going to put a 5 in there. Height is 14. Okay. Okay. Now radius, the change in radius, it says the metal in the sides is 0.05, and the size is 0.05 centimeters thick. So that means that dr, we're going to use 0.05 for that. Okay, and again, R is 5, so we're going to use a 5 for that one. Okay, now here, the top and the bottom are 0.4 centimeters thick, right? But there's a top and a bottom. So the DH is going to be 0.8. Okay, so does that make sense as 0.8?
You timed it by 2.
Yeah, times it by 2 because there's a top and a bottom. So you're looking at volume, and the volume is going to change by, or the height, essentially, if you're looking at the two volumes of the outside of the can versus the inside of the can, then you have to subtract double that. Okay, whereas with the radius, you're only subtracting, you're only going a dr of 0.05. So this is 0.8 here. I think I got the numbers right. Okay, so you just have to plug all that stuff into a calculator, and
34.
let's see here. Plug all that. You got it already? What'd you get?
Yeah, 34.56.
34.56. Okay, 34.56. Whoa, that's an interesting number. Oh no, it doesn't work. What the heck? 34.56. It didn't work for me.
Oh, sorry, I forgot to square the 5. Not just square.
Oh.
It's 84.82.
Okay, 84.82.